Hello, my name is Muhammad Husnain Mubarak, and today I will talk about printed machine learning classifiers. A large number of application domains have requirements on cost that traditional silicon based systems cannot meet. For example, the cheapest silicon based packaged microcontroller is about 35 cents, and even the packageless RFID tags and Java cards have cost in the tens of cents range, which are infeasible for meeting cost requirements of many applications. For example, a beer bottle costs about 10 cents, and the adhesive bandages and packaging labels cost in the sub-cent range. Therefore, businesses are naturally reluctant to adopt traditional silicon-based compute in those applications. Furthermore, many applications require the circuits to be non-toxic, stretchable, porous, and conformable, which can potentially be targeted using printed electronics. A large number of printed applications may need to make classification decisions in the field. For example, a printed smart wound dressing may be used to determine if a wound has healed. A printed pulse oximeter may determine when the oxygenation or pulse rate levels are abnormal. A printed in situ sensor may determine if a packaged food item has expired. We picked a set of seven applications to study for which printed, flexible, wearable, or RFID based sensors already exist. We studied five different classification algorithms for these applications. We observed that the computation in each classifier is dominated by two operations, comparisons, and two input multiply accumulates. The potential hardware cost of each classifier therefore depends on the number of these operations in the trained model and their cost of hardware implementation. We count the number of each operation in the trained model of each classifier and estimate the area and power cost of the classifier. This figure shows the estimated area cost of the classifier in centimeter square. Overall, our results show that simple classification algorithms such as decision trees and regression based SVMs provide a good balance in terms of accuracy and estimated cost. Therefore, we choose to study them for further evaluation. We evaluated two implementations of decision trees in hardware, which correspond to the two ends of the parallelism versus wasted work trade off. The first implementation performs comparisons fully serially, so we call this the serial decision tree. The corresponding architecture diagram is shown in the figure. In the serial implementation, there is a single comparator. There are two ROMs, one for threshold and the other one for classifications. During inference, the working node in the tree is stored in the shift register. The shift register is initialized with value 1, and in each subsequent cycle, the result of the current comparison is stored in the least significant bits of the shift register. Once the initial set bit of the shift register reaches the MSB of the register, we know that inference is complete, and we use the stored index to look up the classification in the classification ROM. Our second implementation performs comparisons fully in parallel, so we call it the maximally parallel decision tree. The architecture of maximally parallel decision tree is shown in the figure. For every node in the decision tree, there is a comparator and two registers. One register holds the threshold and the other one holds the input feature. The result of all comparisons are then used to select the classification using a multiplexer. The results show that inference latency is high, especially for deep trees, almost 200 milliseconds for depth A tree. Area and power overheads are also excessive. For the power requirements of AGT depth A tree exceeds the peak power produced by several printed and hybrid harvesters. The delay, area, and power of the maximally parallel trees are shown in this figure. These trees are on average 1.32 times faster than the serial comparators. However, area and power overheads are excessive when compared to serial implementations. They have 20x bigger and consume 8x more power. The deeper trees consume too much power to be powered by any printed battery or a printed energy harvester. Without further optimizations, printed and hybrid harvesters cannot power any conventional EGT classifier. Serial decision trees with depth 1 and 2 can be powered with blue spark batteries, and in fact, only one depth 1 maximally parallel tree can be powered by printed batteries. Since both NRE cost and per unit area fabrication cost in printed technology are low, highly custom bespoke classifiers that are customized to a model generated for a given application using specific datasets are enabled. Such degree of customization is mostly infeasible in silicon due to high NRE and fabrication cost. We can set the bit widths of our max according to the precision requirements of the network. Furthermore, we can exploit opportunities based on the weight values of the trained network. For example, if some of the trained weights have value 1, we can hardwire our inputs to outputs and save the multiplication logic altogether. And similarly, if weights are 0, we can hardwire our outputs to ground. Such value specific optimizations are exploited in our architectures. To generate bespoke serial decision trees, we explore trees with width 4, 8, 12, and 16 bits for given application and use scikit-learn to calculate the accuracy corresponding to those bits. We pick the tree that gives the best accuracy for the application with minimum hardware cost. In addition, we customize the marks to have the number of inputs equal to the number of input features. We also customize the width of the shift register to be equal to the depth of the tree. Size of each entry in the threshold ROM is customized to the width of the threshold value. The classroom size is customized to match the number of classes. To generate bespoke maximally parallel trees, the registers that are used for holding thresholds and inputs in the conventional architecture are removed. We train all trees using our scikit-learn framework to get the trained threshold values, which we then hardwire in the RTL. The input feature registers are replaced with connections directly to the input feature port. Now that the actual trained threshold values are hardwired, the comparators have only one variable input, which greatly simplifies the overall design. We use the same methodology as bespoke serial trees to finalize the bit width of the trees. Figure shows the delay, area, power analysis of EGT bespoke serial trees relative to conventional serial trees. On average, EGT bespoke serial trees have 1.2%, 37%, and 22% improvements in latency, area, and power. Our results show that the bespoke maximally parallel decision trees perform much better in all measures compared to their conventional counterparts. On average, latency, area, and power improve by 3.9x, 48x, and 75x respectively. Finally, to demonstrate the feasibility of printing bespoke classifiers, we designed and fabricated a decision tree of depth 2. A microscope photo of the fabricated circuit after printing the EGTs is shown in the figure. To test operation of the prototype, all output class labels were measured against all possible input signals. To the best of our knowledge, this is the first quantification of the benefits of bespoke classifiers in printing technology. Also, this is the first prototype of a digital decision tree in printed technology. In several printed technologies, including EGT, ROMs have low area and power overhead. For example, 1-bit EGT ROM has an area of 0.05 mm square, while 1-bit inverter has an area of 0.22 mm square. Corresponding power values are 3.13 microwatt and 9.6 microwatt respectively. This is due to the fact that ROMs can be built simply as crossbar architecture where the cross points are shorted by printing a conductive material. This opens up the possibility of implementing classifiers using lookup tables where computation logic is replaced by lookup tables. In trees, we can replace our comparators with lookup tables. As an additional optimization, we can also use bespoke ROMs. When a bit is stored in the ROM, when bit which need to be stored in the ROM is set, we print a dot register at the cross point of the column and row. When a bit is clear, no dot is printed, resulting in infinite resistance. Since the dot resistors are much larger than a wide crossover point, clear bits consume practically zero area. In serial decision trees, there is only one comparator to replace and none of the inputs are used simultaneously. So ROMs are not a good fit for logic replacement. The area and power overhead of individual lookup based comparators were 6.7 times and 7.3 times respectively compared to the non-lookup based comparators due to the decoder overhead. In parallel decision trees, however, there are often many comparisons using the same input feature, leading to significant decoder reuse. This figure shows the architecture of lookup based implementation of maximally parallel decision trees. In figure, we show that latency, area, and power benefits we obtained from replacing all the comparisons in the EGT parallel decision trees with lookup-based equivalents. Results are normalized against parallel trees implementation. In many cases, especially with shallow trees, there is not enough input feature reuse for the lookup tables to be useful. But in best case, we get 13%, 38%, and 70% improvements in delay, area, and power. This figure shows the impact of bespoke ROM optimization for EGT maximally parallel decision trees. Area and power benefits are increased by 52% and 12% respectively compared to non-optimized lookup-based implementations. One effective method for significantly reducing the transistor count and therefore overall area and power overhead could be to substitute complex logic by small analog circuits with only few transistors. For some applications, an analog classifier may also allow sensor outputs and inputs to be connected directly to the classifier itself, therefore avoiding costly ADCs and DACs. In silicon-based classifiers, such substitutions are practically challenging due to A. Additional verification and test challenges, and B. Noise and mismatch constraints force the analog devices to be large, and therefore any area and power benefits may be lost. In printing technologies, however, low fabrication costs allow iterative refinement to fix the noise mismatch issues. Therefore, such analog substitutions may be more feasible. The fabricated two-level decision tree consisting of one root node and two split nodes is shown in the figure. It has 11 EGTs and 3 printed registers. The worst-case output signal of the split node are clearly distinguishable, and hence the printed analog decision tree is functionally correct. This is the first prototype of an analog decision tree in printed technology. In this figure, we show that the optimized analog and digital classifiers are placed into sets based on which sources can power them. For each decision tree depth, we pick the set for the power source that can power all bespoke benchmark variants. For example, Molex printed batteries can power all depth for digital decision trees for each benchmark. Harvesters are now capable of powering several decision trees. A large number of application domains have not seen much penetration of computing due to the cost, conformity, and toxicity limitations of silicon based systems. Recent low voltage printed computer systems have the potential to address these limitations. We found that decision trees and SVMs provide a good balance between accuracy and cost. Subsequently, we evaluated conventional decision trees and SVM architecture in those technologies and concluded that their area and power overheads must be reduced for them to be feasible in printed technologies. Then we explored several printed specific classifier architectures that exploit the unique cost and implementation trade offs in printed technologies. Our evaluations showed that bespoke EGT printed classifiers are feasible under certain realistic constraints. Furthermore, lookup based classifiers outperform their non lookup equivalents, and analog printed classifiers provide additional benefits over digital bespoke counterparts. Our results and prototypes demonstrate the feasibility of fabricating and deploying battery as well as self powered printed classifiers in the application domains of interest. Thank you.